All right, chapter 10.1 deals with exponential functions. And what we're going to do is it's a kind of a review of the things we've been doing, except we're just going to add more complicated looking exponents into our operations. And I think you'll kind of get the hang of what we're doing as soon as we do some examples here. So it's actually really easy. We're just going to jump straight in. If I gave you 2 to the rad 2 power, right? We've never seen a radical in the exponential area before, but the operations are still going to stay the same. If I say 2 to the rad 2 power and I take that to the rad 8 power, just like the rules of exponents tell us, I'm going to multiply those exponents together. And you just got to remember that when you multiply radicals, you multiply the inside, so it's going to be 2 to the rad 16. And we all know that rad 16 is 4, so it's really 2 to the 4th. And 2 to the 4th is actually 16 itself. So that's how you get the answer to that one. The next one here, same idea. If I go 7 to the 3 rad 2 times 7 to the 4 rad 2. Well, remember, when we're adding two things that are of the same base, the base carries over, and then I just add the exponent. So it's going to be 7 to the 7 rad 2. And that's as far as I can go with that problem. So based on that, if I gave something like, say, 12 to the 6 rad 3, and I asked you guys to divide by 12 to the 2 rad 3. Well, remember what we do is we just carry the base over, and we subtract our exponents. So 6 rad 3s minus 2 rad 3s is 4 rad 3s. Whoops. And that 3 is ugly, so we fix it. Now, the only thing they can really do to make this harder would be to give you something that looks kind of like this. If they said 5 to the rad 3 times 5 to the rad 27, and they asked you to add those two exponents, well, again, we know that the base is going to carry over. The hardest part of this problem is understanding what rad 3 plus rad 27 is. Well, rad 27 is really 3 rad 3 plus another rad 3, so what I have is 5 to the 4 rad 3 power. And then the other thing they can do to make this more difficult would be to give you different bases. Well, if I say 81 to the rad 7, times 3 to the 2 rad 7, well, what you got to do is now we have to start altering the bases, right? Now, 81 and 3 have a common base, and that base is 3. So I'm going to go ahead and carry down the 3 to the 2 rad 7, keep that exactly as it is. Well, 81 is really 3 to the 4th. And that 4th is being raised to the rad 7. Well, from here, we just go and use our properties of exponents to multiply those together. So I get 3 to the 4 rad 7 times 3 to the 2 rad 7, and now I'm back to where I started. I should end up with 3 to the 6 rad 7. All right. Okay, so let's move on to the next little bit, which is solving some equations, getting the bases the same. This idea of getting the bases to look the same is going to come up frequently in this chapter. So make sure you guys understand your bases of exponential functions. Okay, number one. If I say something like 5 to the 3x is equal to 5 to the 4x minus 5, well, since the bases are equal, right, I'll even say for equations we need equal bases. Well, since the bases are the same, the exponents are going to be the same. So what we can say here is that 3x equals 4x minus 5. Do a little bit of algebra here. I'm going to get negative x equals negative 5. Therefore, x equals 5. All right. So again, if we do something like, say, 7 to the 2x minus 11 equals 7 to the 3rd, bases are the same. So I get 7. Oops, not 7. I get 2x minus 11 equals 3. Add 11, divide by 2, x equals 7. Number 3 here, if I say 5 to the n minus 3 equals 1 over 25. Here's where the things are going to start getting a little more difficult. remember, I have to create similar bases or same bases. So I can identify 1 over 25 as 1 over 5 squared. And then I can parachute this 5 squared up to the top and make it 5 to the negative 2. So after I clean all this up, what I should really have is 5 to the n minus 3 equals 5 to the negative, to the negative 2. And since, again, I have same bases, my exponents are going to be the same, so n minus 3 equals negative 2, n equals 1. So again, the only thing they can really do to make this harder is to make you manipulate before you get to a point where you can solve equations easily. So let's do a few more of those, and then we will move on to something else. So if I say 9 to the x equals 27 to the x minus 1, I've got something similar here. I mean, 9 and 27 have something in common. They have a 3. So I can say it's 3 squared to the x power equals 3 to the third, and that's being raised to the x minus 1. Well, 3 squared to the x is really 3 to the 2x. The only thing you got to be careful of here is that you have to use the distributive property. So this really, when we multiply it together, becomes 3x minus 3. So I have 3 to the 3x minus 3. I'm back to the same bases going on. They're gone. I have 2x equals 3x minus 3, and so x equals 3. All right. I believe that was example number 4. So let's go ahead and take care of the last example, example 5. Clean some stuff up here a little bit. Okay, in example 5 here, I have 1 over 9 all to the m power, and that's going to equal 81 to the m plus 4. Well, again, I need to mess with both of these. And so, let's see, I can make them base 9. That would be easy. So 1 over 9 is really 9 to the negative 1 power to the m power equals 9 squared to the m plus 4 power. So I get 9 to the negative m equals 9 to the, remember to distribute, that's 2m plus 8. So what I get here, if I move this guy over a little bit, is I get negative m equals 2m plus 8. I'm going to go and subtract 2m from both sides. I get negative 3m equals 8, so m equals negative 8 over 3. So again, the hardest thing they can do is to give you unlike bases. And so make sure you guys are getting the bases the same and solving your equations and simplifying your expressions. All right, see ya.